Today's lecture is devoted to practical examples of groups. Now there are lots of different examples of groups that one can produce artificially, and those are often used in various examinations, but this video will focus specifically on practical examples of groups. Possibly the most important type of groups that occur in practice are the groups of symmetry of an object. We have already seen an example of group of symmetry when we talked about the example of the triangle. So let's quickly review that example. We started with some object. In this case, it was a triangle. And then we considered a frame around that. So here it was a two-dimensional object. So I could say, I write it like this. I draw a frame around that object. And I also label the corners by various numbers so that I can remember how this triangle was originally placed. And then what I want to do is I want to place the same triangle differently but fitting that frame. I can fit it directly like this. This we call the identity element E. I can flip it like this because it's an equilateral triangle. It will fit again. I can flip it like this. I can flip it like this. I can rotate, and all these different things form a group. That is the group of symmetry of an equilateral triangle, and we have seen that there are exactly 6 elements in it. Now, this idea of group of symmetry has nothing to do specifically with triangle. It is applicable for anything two-dimensional or three-dimensional. Now, when we describe something, some particular shape, we often talk about how symmetric it is, and the mathematical way of capturing that is through group of symmetry. Take, for example, a rectangle. So let's see what is the group of symmetry of this rectangle. So I first take a rectangle and fit it there. So if I just fit it directly, that is my identity element, which I shall again denote by the letter E. Now what I can do is that I can take this and flip it horizontally and fit it back again. Let it give it a name, call it H for horizontal. I can do the same thing but vertically, flip it like this, and that will give me V. I can rotate it. I can rotate it 180 degree in the counterclockwise direction, call it R. And I can do it in the opposite direction, since I have already called it R, the other thing R, well, let me call it L. You understand that R and L are inverses of each other. So these are the different ways by which you can take this and put it back. And you can of course combine these things. For example, you might first do H and then you can do V and see what comes out of it. Now it is always going to be the case that if you combine these basic operations, these basic moves, in that case you are again going to get back to one of these things, because these are all the different ways in which you can take this rectangle and fit it back. So if you can take it, do something and fit it back, again take it, do something else and fit it back, then the composite effect will be to fit it back again. So the closure property must be there. If you take any two, follow one with the other, you must end up with something again in the list. And this is bound to be a group irrespective of what particular object you start with. Now let's compare this with the case of a square. Just intuitively we can feel that a square is more symmetric than a rectangle is. Now how do I quantify that? Well, I take a square. I can do whatever I did in case of the rectangle, because a square is a rectangle. So I can keep it as it is. I can flip it horizontally, can flip it vertically, give it a rotation and rotation 180 degree rotation. However, I can do more things. I can take the square and rotate it just by 90 degrees. That is a new thing which was not possible in case of the rectangle, because if I take this rectangle, rotate it by 90 degrees like this, it is not fitting into the frame because the length is not same as the breadth. So in this case, I have some extra operations that I can do. So let me call it R90. Of course, you can still do R90 twice. In that case, you get to this R. Similarly, I can do L90. And if you can do R90, you can also do R270, which you can feel is same as L90. Well, if I turn it 3 times, 1, 2, 3, that is same as turning it only once like this. Now you can do something more also. You can take this and flip it along this diagonal. That will also place it in the same way. So I will call this D1. I can flip it along this diagonal also. That will do it D2. Thus the group in this case is larger. And this size of the group of symmetry actually is a quantitative way of measuring which shape is more symmetric than which other shape. So this intuitive idea that a square is more symmetric than a rectangle can be made precise in this way. Now here is a shape that has got no symmetry at all. You can see that it is not symmetric in any direction. As a result, if you cut it out and you want to fit it back, the only way you can do it is by putting it back just in the original way, which means its group of symmetry consists of only the identity element. So it is the smallest possible thing, which basically says that this has no type of symmetry associated with it, except of course the trivial identity symmetry. The concept of a group of symmetry extends even to 3-dimensional objects. For instance, here is the water molecule H2O. Now when chemists describe a molecule or the shape of a crystal, they do not have enough names for different shapes that might occur in practice. So they cannot always describe things like saying it is a cube or it's a tetrahedron or things like that. There are so many different shapes. So instead they describe the shape in terms of its group of symmetry. So let's take this particular molecule. What are the different types of symmetries that we can think of? In this case, just imagine that this is floating in air, and what you can do is you can take it up and put it back again. That will give you the obvious things, that is the identity symmetry. Then what you can do is that you can imagine an axis like this and just turn it around by 180 degrees. So this hydrogen will go there, that hydrogen will come here, and that, let me call it, say, R. So if you apply R again, you get back to your original configuration. Now imagine that there is a plane which just cuts this completely through the center. In that case, you can say that there is another type of symmetry here. You can reflect it along this particular plane. So you can reflect it like that. In practice, you cannot really do the reflection because it is just like imagining as if whatever is behind the mirror comes in front and whatever is in front of the mirror goes behind the mirror. So it's more like a conceptual operation, but you can think of it. And let's give it a name. Suppose I call it S, or I will call it S1. Now similarly, you can think of yet another way of reflecting. This time, I will take the plane like this. So it is perfectly symmetric. The reflection of this hydrogen is that hydrogen. Similarly, if you reflect that, you will get this hydrogen, and the oxygen is perfectly split in half. Now, if I reflect with respect to a mirror like this, in that case, I will again get a molecule which will be indistinguishable from the original molecule. I will call this symmetry S2. And you can easily convince yourself that these are all the things that are there. So if you combine any of these things, you are bound to get back one of these 4. For example, I can easily see that R square is actually identity. You rotate twice, 180 degree, then you get back to the original position. Similarly, for both S1 and S2, If you take their square, it will be the identity, and you can work out the rest. So the group of symmetry of the water molecule consists of these 4 different elements. Now here is a different type of group which I have called group of motion. Just as we had group of symmetry of an object, we can have group of motion of an object. Now here is a particular object that should be familiar to all of us. It's a Rubik cube. Now in a Rubik cube, you are free to rotate the different layers. So you can rotate the top layer like this. Now if you rotate things in this way, then you can describe all the motions that you can create on the Rubik cube as a group. It's often referred to as the Rubik cube group. Now the way that idea occurs is because of this. These are all the basic motions. So if I just write down the different sides as up, down, left, right, it of course depends on how you are looking at it. Say if I am doing it like this, then I will call this up, call this down. You might call it top or bottom, maybe that is better. So top and bottom, and you have got left. Similarly, you have got right, and let's call it front, and you have got back. Oh, then possibly up and down was better terminology after all. Otherwise, notation clash. So F and B. Now for each one of them, you can turn it by 90 degrees, either in this direction or in that direction, and you can keep on doing that. So I will denote by the letter U the motion which turns the top layer 90 degrees clockwise, say, when you are looking from that particular direction. So if I am rotating like this 90 degrees, then I will call it U. So I have U squared, which is rotating it 180 degrees, and I have U cube, which is rotating it by 270 degrees, which is same as rotating it in the opposite direction by 90 degrees, which is U inverse. Similarly, for I can have B inverse, L square, R square. I even have something like R to the power 100, which means you keep on rotating the right face 100 times, which effectively means you restore it back to the original position, because for every 4 applications of R, you get back to the original thing. So everything that you can construct, all the motions are constructed out of these symbols, U, B, L, R, F, B, together with the powers, and the powers may be either 1, do it once, do it twice, or do it -1 times, it's inverse. Any other number will actually reduce to one of these things, or you may not do it at all. For example, a typical move may be L, B, R inverse, U square, which means turn the left side once, then turn the back side once, then this right side in the opposite direction, and give a 180 degree turn to the top thing. So you can write things in this way. And you can easily understand that these things, all these things will form a group. That is called the group of motion of the Rubik cube. When we discussed group of symmetry, I mentioned that every object, every rigid object, 2D or 3D, has a group of symmetry. But not all types of things that can be moved form a group of motion. You need a certain condition for that, and that condition should be you are always having the same set of alternatives at every step. If that is violated, you cannot describe that set of motions by a group. Here is one example. Suppose this is a maze. So these are roads and these are junctions, and you are standing at some point. Now if you are standing here, what are the motions that are possible? You can go up, you can go down, up by 1 step, down by 1 step, you can go right, or you can go left. Now I cannot say that the set of all possible motions that can be constituted by combining these forms a group. For example, I have this motion. I can do U, R squared, then L, and then D. So this is a particular motion, which means go up, right, left, and then down. That is a valid motion. However, there are points where all these four motions are not available to me. For example, if I apply a left, I come here. From here, I cannot apply L anymore. So if I am starting here, L square is not a valid motion because it will take me out of the maze. So in this case, all the possible motions do not form a group. In case of the Rubik cube, that was not a problem because we were rotating. In every step, we could have all those possible different motions. In this case, we do not have that. Well, in the next video, we shall continue our discussion of different types of groups that occur in practice. So I will not extend this video any further.